I will begin. Dear Father, we thank you again for this opportunity we have just to meet together and study your creation. Thank you for the break and for the relaxation, I hope. And I just pray you help us to use this time wisely. Again, Lord, that we would glorify you, what we do, Lord, this day. In your name I pray, Lord Jesus. Amen. So I will not give you guys a quiz today. Relax, despite the threat. I think Wednesday is when we'll have that quiz. All right, and then I hopefully will give you that take-home quiz that's mentioned on the syllabus. And I don't anticipate that the that the take-home quiz is like soul-crushingly difficult or anything. It's just that there's not time for an in-class quiz, you know. So I wanted to work a couple things for you guys today, and so I'm going to start with what's called the centroid of a curve. And this is closely related to the notion of center of mass. So the centroid is the center of mass if the mass density is uniform, if it's constant. So here's basically definition. This definition is from page 521 of your book. Here it is, x bar L equals to the Oh, there's a typo in your book. I was looking at your book and there's no equals here. I was just writing equals because there should be an equals there, but at least in my book there's no equals. I want a refund. Let's see here. Curses. Why is he using big X? There's some weird typesetting here. X of S, ds, and y bar L equals the integral from 0 to L of y of S ds. I think I just got fished into what I didn't want to write. Yes, okay, so he claims these are geometrically natural definitions. So let me just try to tell you what we're doing here. We've got some curve, and it's got some length, all right? Length L, and what we're trying to do is to describe what's the geometric center of this. Like, so I made my example too hard for you to see. Let me fix it. So if it was something more like this, I would do better. So where is the center of this curve? It's not on the curve, right? So it's something like, just eyeballing it, something like here. Like I said, so this would be the coordinates of x bar, y bar. This is the so-called centroid of the curve. If you want a physical explanation, if the curve has equal density, this would be its center of mass, right? So his initial definition is in terms of arc length, all right? The arc length parameter. So his parameter is like s equals to 0 here, and then over here you've got s equals to L perhaps, right? So a point in the middle would be parameterized by x of s, y of s. And he's saying you do those integrals with respect to arc length, that gives you the centroid. Now, a lot of times, we don't have an integration, we don't have a parameterization of the curve with respect to arc length, right? Usually, if you want to parameterize a curve with respect to arc length, it actually takes a fair amount of work to find such a parameterization. So this isn't of particular calculational use to us. And so basically what we want to do is use a corresponding derived result. And so basically we want to switch these to a parametric viewpoint with arbitrary parameter t. I mean, okay, so this is already a parametric viewpoint, but the parameter is very special. The parameter in those is arc length, right? So to relate ds to dt, how do we do it? Well, we have this already, right? ds is equal to, well, it's equal to v dt, right? Which is what? The square root of dx dt squared, right? Plus dy dt squared dt. So like my ds in these formulas, I can convert to dt by multiplying by speed. And so basically there's what we're going to do. So here's our typical formulas for finding a centroid of a path. So if r of t equals to, say, x of t, y of t, for a less than or equal to t less than or equal to b, then, of course, the length of the path we get from what? The integration from a to b of what is it? The square root dx dt squared, right? Plus dy dt squared dt. We talked about that before the break. That's the arc length, right? The total arc length. I'm using an L4 now. And as I was saying, I'm trying to unravel some of the book's comments on pages like 521 to 522. So on the other hand, we could also look at it this way: x bar is equal to 1 over L, right? Integral from a to b of x of t, square root of dx dt squared. I hope you're seeing something. If you actually have a specific problem, what should you do? Man, you want to calculate the speed, right? And find the nicest formula you can for it before you actually go much further, because the speed is going to appear in all three things we're looking at here. The length of the curve, and also these formulas for the y-coordinate and the x-coordinate of the centroid. Okay. So basically, if we can do these integrals for a given path, then that allows us to find the center of that path. Let's look at a specific example, if you guys don't mind. Let's consider a half circle. Radius r, centered at origin. Have I already done this? I don't think I have. Find the centroid. See, that's the very bad thing. Sometimes I watch videos from like last year, and then it really messes with my head, because then I get it in my brain that maybe we did that this year. I mean, this semester, which is not helpful to me. It's a danger I didn't realize. I should not watch old videos from the same course in the same semester, unless I'm really, really awake. Anyway, this is an interesting problem. I hope I have not solved this before in here, have I? No. What I did the other day, and I do remember this, is I started to try to find the centroid of like the laminar region, so like a solid half circle, half disk, really. And then I remembered, oh, there's these awful formulas involving the cube of the polar radius to find those. And I really actually don't even want to talk about that. Again, it's not that interesting. It's one of those homework problems in Salis and Hilly that I'd just rather forget. So let's do that. I mean, those are weird, obscure formulas that I can later obtain in Calculus 3 from much, much more beautiful arguments. Okay, so in order to find the centroid, what do we have to do? Well, first order of business, we need to parameterize this path, right? And to be clear, I'm not talking about this down here. I'm just talking about the circle, the half circle, okay? If I were to add in that diameter at the bottom, I would have to do further calculation, right? So what's the parameterization? If I pick a point here, right, and I ask you what should x of t, x should be equal to what, y should be equal to what there, what do you think? I'm going to tell you that 0 is less than or equal to t is less than or equal to pi, if you don't mind. It's kind of a big hint. Geometrically, we can do what? We can use the standard angle as a parameter, right? And so the natural parameterization, I think, is just what? R cosine t and R sine t, am I right? So, well, so what? Hence, what's dx dt? Dx dt squared plus dy dt squared is what? So we have minus r sine t squared, and then plus r cosine t squared. We add them together. That gives us r squared, sine squared t plus cosine squared t. I have this deja vu feeling here. I feel like we've done this before. But the reason I have that feeling is because we calculated the circumference of a circle before, right? And the same calculus comes up there. I mean, in fact, sine squared plus cosine squared being 1 is really the hero of us getting anything done in this part of the course, isn't it? Like, if it wasn't for sine squared plus cosine squared being 1, we'd be in a lot of, well, we would just lose half of our interesting examples, I think. So, thankfully you guys know that, right? Okay, so then what? This is the speed. So to find, I guess, first of all, we got to find the length. I mean, I don't really need to do this. You could tell me the length already. What is the length of this curve? Right, and that's because the integral, so this says that the speed is just equal to r. You notice these formulas can be rewritten as the integral from a to b of v dt. This is the integral from a to, well, 1 over L. Integral from a to b of x times v dt. This is 1 over L. The integral from a to b of y times v dt. So basically we just got to find the speed. The speed here is constant in r. So you said r pi? I will agree. Or maybe you said pi r. I still agree. So there's the length. Now let's calculate. Now this is dumb, but I'm going to do it anyway. X bar, 1 over L. What is L? Pi r. Integral from what? From 0 to pi, right? What's my x? R cosine t. And then my speed, r dt. So what do we get? We got ourselves an r over pi, right? And then minus the cosine of t evaluated from 0 to pi by fundamental theorem of calculus, part 2. What'd I do? Oh, goodness gracious. Sadness. Yes, sine. Yeah. Oh, and it's not negative? Yeah, it's not negative. That's right. Thank you. Matthew's favorite saying at the moment, my youngest son, he's like, no not, no not, no not, which doesn't mean yes. It means no, no. But, you know, logically speaking. So this is, anyway, yeah, okay. So that's 0, right? Because sine of pi is 0 and sine of 0 is 0. And this we could have done without any calculation, right? If a problem like this is on your next test, I'm perfectly fine with you going, by symmetry, the centroid's x-coordinate is 0. See? Because it's clear that in the x direction, by symmetry, the centroid has to lie right in here, right? Because this shape has symmetry with respect to the y-axis, right? Okay, so then the interesting part, what's y bar? R sine t r dt. So now we get ourselves r over pi minus cosine t evaluated from 0 to pi, which gives us what? I believe that gives us 2r over pi, right? That makes sense, right? This is less than r, right? Because 2 over pi is a number less than 1, right? And that makes sense because that says that I'll draw it over here. Basically, the centroid is, I don't know, somewhere in here somewhere. So the centroid doesn't actually lie on the half circle, but it's the point which is in the middle of everything, right? Any questions? So if you're at, center of mass problems are a little bit different. What's the difference with center of mass? In center of mass problems, you're possibly given a variable mass density to the wire or rope, whatever you want to think of it as, and there's a density factor which will appear in these integrals. All right. Tell you what, maybe I'll do that tomorrow. Let this sink in here for now. What I want to talk to you about now is what's called surface area of a surface of revolution. So, draw some pictures for you. So what is it?
I was just thinking we did this earlier in this class.
Well, did we do this earlier in this class? Maybe we...
I'm sure we didn't do surface area.
No? We have done volume. Yeah. So this is section 10.8, area of a surface of revolution. Actually, I'm back a few pages, funny enough, but there's a reason for that. So basically here it is. If you have a curve, I'm just going to kind of describe for you guys the setup, and the curve looks something like this, whatever, then you can revolve it around the, I'm going to just talk about the, we could talk about revolving it around various different axes, but we'll just stick with the x-axis, okay? So if you revolve this curve, given curve between, say, a and b, x equals a and x equals b, and so if you revolve this curve around the x-axis, you get what's called the surface of revolution. So you can kind of imagine, I'm just not sure if it, I'll try. Like that. I mean, this is the revolved curve, which I usually draw dotted. And if you can imagine, there's it's going out of the board, I mean, I'm not very good at drawing these, but so it's a surface of revolution. You take a curve and just imagine revolving it around the x-axis. This gives you a surface, all right? And the question is, what's its surface area? If you could imagine laying little squares of paper on this, really tiny squares, and just covering the whole thing with little malleable squares which didn't change the area as you stretch them. And you cover that whole thing, like what's the area of those, how many of those little squares do you need, right? Or if you could somehow take like a rubber sheet and stretch it around the surface such that the rubber sheet maintained its area in the stretching. Somehow it's compressed and stretched at the same rate in different parts of the rubber sheet. What's the area of that rubber sheet? That would be the surface area. Anyway, I think you guys know what surface area is without me trying to give you some kind of silly physical analogy. So the question is, how do you calculate that surface area? And the answer is again given to us by arc length. So what we do is we divide it up into basically little ribbons. I'm going to draw one down here. Sort of like this. I might have talked about this another day. I have the worst case of deja vu in this semester. I tell you what, wrong concavity. see here. Man, I'm having a mental block in terms of my picture. Try this again. Just don't like it. Sorry. It's just my stupidity. Anyway, the question is, what's the area of this? You know, what's the area of this band? And so it's convenient to think about that in terms of, first in terms of arc length. So basically, the little bit of area from that is going to be given by 2 pi y times ds. So 2 pi y is what? 2 pi y, you know, this distance here is y, right? So we're assuming that this is, you know, for the purpose of the discussion, this is y equals f of x. But you could say that, I mean, you could say, I don't really want to say that. That's, I mean, fine, you could say that, but I'd rather say that this is given by x is in terms of parameter and y is in terms of the arc length parameter. So it's parameterized with respect to arc length for our convenience geometrically. So the little bit of area from that one little ribbon there would be 2 pi y ds, right? Because that's the circumference here, and then that's the thickness of it. And you can imagine taking these little ribbons and covering the whole surface of revolution with them. And then, of course, we just have to integrate those to get the whole surface area. Now, again, we don't want to actually calculate with respect to arc length, so we convert this to time parameterization by the usual switcheroo, which is just this, 2 pi y times ds dt, but ds dt, of course, is what? Square root of dx dt squared plus dy dt squared dt. And that would, of course, be for, you know, t1 less than or equal to t2, t1 less than or equal to t less than or equal to t2, where, you know, this is x of t1, y of t1, the initial point, right? And the final point over here being x of t2, y of t2. So if I can parameterize my profile curve, which we revolve around, then I do this to find the little bit of area corresponding to the little change in the parameter dt, and then I'm going to integrate that from t1 to t2 to find the total surface area, right? So summary, surface area equal integral from t1 to t2 of 2 pi y of t square root dx dt squared plus dy dt squared dt. So you're like, yay, another integral, woohoo! No? Yes? Oh, okay. You guys look thirsty for calculus. You're like a whole week away from it. You're like, Thanksgiving was awful. I had no calculus.
Except for you're studying calculus the whole time.
You're studying calculus the whole time. Yes, I was much like my abstract algebra students, who all of a sudden know more about field extensions than I do, which wouldn't be that hard. I don't know that much about them, but somehow I think this did not happen. But let's see here. So, let me record for posterity the the centroid here was what? It was 0, 2r over pi. All right. So I'm going to erase this. Let's calculate the surface area formed by revolving this half circle around the x-axis. What is that? It's a what? So you could write this rotating r equals to r for 0 less than or equal to theta less than or equal to pi around the x-axis, right? That's another way I could have characterized the half circle. You say sphere? I think that should be right? So if we take this circle, half, that was supposed to be a half circle, I'm trying, the radius r, and if you rotate that around, of course you get, the whole deal, right? So we can calculate, it's this anyway. Here's my standard picture of sphere. There, like that. Man, I got some work to do before Calc 3, guys. I don't know. My three-dimensional drawing it's not where it needs to be at the moment. I'll have to do some thinking. Anyway, so this is a sphere. So let's calculate. We already know the parameterization, right? So we have x equals to r cosine t, y equals to r sine t, 0 less than or equal to t less than or equal to pi, and we just calculated just a second ago v is equal to r here, right, from example 1. So we don't need to reinvent the wheel. We can just keep spinning it. And so now what do I got to do? I just got to do that integral, right? So what's the surface area? Integral 0 to pi, 2 pi y. What's y? R sine t, right? And then I'm supposed to multiply that by the speed times dt. The speed here, right, is just r. So there you go. We've got 2 pi r squared, the integral from 0 to pi of the sine of t dt. My brother says that every Calculus 1 student should just internalize the fact that when you look at sine and you look at one of its nodes, you should immediately go, that's 2. Because this comes up so much in calculus. The fact that the area under 1/2 of the sine function is 2. Right? But anyway, let's derive it again for the 100th time in your calculus experience, probably. Minus cosine t. Oh man, I can't do math. Cosine t, no. Minus cosine t, I'll eventually decide. 0 to pi. So we get 2 pi r squared minus cosine pi plus the cosine of 0, which of course is minus 1, so it's 4 pi. Of course well, I was about to say the familiar result, 4 pi r squared, but I don't know, I'm not sure. Do you guys know that before I told you? Show of hands, who here knew that the area of a sphere was 4 pi r squared? You've seen it before. I mean, I'm not saying that you've derived it before. I'm saying how many people here have actually heard of this formula before, the area of a sphere, 4 pi r squared? A good number of you, right? You've seen this in physics, certainly, right? This is important to, if you don't know this for Gauss's law in second semester physics is all about this formula, right? But there it is. Now, here's an interesting thing. What's the relation between this surface area, right, and that centroid? Find the centroid and treat it like a cylinder of that radius. How long should the cylinder be? So you want to re-envision the sphere as being a cylinder with the radius of the centroid, right? Which would be, 2r over pi. That radius. So we want some length here, right? We call it L. So 2r over pi times L equals to 4 pi r squared, right? So what should we make L? I think I've done this wrong because I need, excuse me, what should the, just a second here, what should the area of a cylinder with length L and radius 2r over pi be? It shouldn't be this. This is not the area yet, right? This is the radius times the length. I'm missing a what? A 2 pi, right? Right. So this cleans up to what? 4RL equals to 4 pi r squared, or what? L equals to, what is it? Pi r? What is pi r? Pi r is the arc length of the curve which is revolved. This is the theorem of Pappus. To find the surface area of a surface of revolution, just take the curve arc length and multiply by the centroid. It's kind of cool, right? So that's another way to think about the significance of the centroid. In some sense, weird, right? And yet not. I mean, so like, if you could somehow trade the sphere for a corresponding cylinder with the same area, that's what the significance of the centroid is in part. It tells you the radius of the cylinder you should make, assuming that you make the length of it the arc length of the curve that you're revolving. It's actually kind of cool, right? I mean, if somebody asked me, here's a basketball, make me a roll of paper that has the same area as the basketball, I guess I could do it by just the formula 4 pi r squared and picking a radius, right? But the fact that you can do it like this is with the connection to the centroid and the arc length of the curve is pretty cool. I think if I remember right, I think last time I taught Calc 2, I had a student notice the theorem of Pappus on his own, just in the middle of an example. Like we were working out something and something else, and then he's like, "Isn't that and that related in this way?" And I was like, "Whoa!" So I decided to work it into this lecture for you guys because I think it's pretty neat. Anyway, that's in your book. At the end of section 10.8, Pappus' theorem on surface area, which he states as A is equal to 2 pi r bar times L, where r bar is the distance from the axis to of revolution, the distance from the axis of revolution to the centroid of the curve. So, well, I mean, we can work more examples if you want. That's the main thing I had to tell you guys today. You have questions about homework, I certainly have time for them now. You guys are killing me. Is this how Calc 3 is going to be next semester for me? Just be talking to myself the whole semester? I'm gonna have to make some 3x5 cards and put your names on them, and I'm just gonna start pulling them out and going such and so forth. What do you have to say about this example? And if you don't have anything to say, -5. No. Sorry. I won't actually do that. I'm just talking. What's that?
Did a practice at a middle school here, and she had all the students' names on popsicle sticks and top, and she pulled the popsicles out.
Names on a pop.
Sticks, and they would have their name on it, so she filled out. So it'd be kind of funny to have to do it.
See, I don't, generally speaking, like to call on specific students in class because, like, everybody processes things differently, and not everybody, even if they understand completely what's going on, wants to say anything in class, and I respect that. Like, I don't want to force you to talk in class, right? But on the other hand, there comes a point where when there are no questions, it wears on me.
How practical is it to use the theorem of Pappus, though? Like,
Oh, probably not.
you have to calculate both the arc length and the centroid.
Yeah.
Much more complicated.
Yeah, I mean, but it's neat. I guess the other thing is, of course, this guy is, it's not like, oh, Newton came along, Leibniz came along, and then 50 years later they noticed this. No, like this guy is from hundreds of years before. He did this without modern calculus. He just saw it. We forget sometimes some of these things we're doing have origins back before we had this calculus. So, all right, let me work some examples for you then. Let us let's look at y equals to cosh of x for x an element 0 to natural log of 2. Find area of the surface of revolution. This happens to be number 18, section 10.8. Okay, first of all, what is this? Let me just draw a picture for you guys. Cosh is what? It starts at 1. In fact, that's the smallest cosh ever gets, right? So cosh is 1, and then it just grows exponential, basically, like that. And so this is something like I don't know, kind of like the end of a horn or something. I don't know. So basically, that's. I should not draw this back thing. This is what's ruining my picture. I just get it in my head. I have to draw the back dotted line. I don't have to draw that dotted line. If I don't draw it, it looks better. So anyway, here's the curve. Here's a typical band on it. Not that I really need to draw that, but there it is. Anyway, so what's the surface area of this thing? Now I've ruined it. Oh, I fixed it. No, I'm ruining it again. Anyway, you get the idea. So here we go. Parameterization, right? So basically I would say I'll use, good grief, I cannot spell in any of my classes today. Use x equals to t, right? And y equals to cosh t, if you like, as a parameterization. Or if you want, you could leave t equals to x. It's up to you. I'm going to put an x equals to t to emphasize conceptually what's going on here. Now, dx dt is equal to 1. dy dt is equal to sinh t, right? So that means that dx dt squared plus dy dt squared is what? Looks like we're going to give the Pythagorean identity a break and use the hyperbolic Pythagorean identity instead. 1 plus sinh squared is, in fact, cosh squared t, right? Because cosh squared minus sinh squared is 1. So the speed the speed of this this path is just cosh t. Cool. And let's see here. Thus, the surface area should be equal to the integral from, looks like 0 to log 2 of 2 pi, what's y? Cosh t, right? And then times cosh t dt. So here, this is y, this is the speed factor, okay? Just happens that the y and the speed are the same. It's kind of cool. So, okay, well that's 2 pi integral from 0 to log 2 cosh squared t dt. Well, we know this integral. We've seen it before. This is going to be pi integral from 0 to log 2 of 1 plus the cosh of 2t dt. What happened to my 2 up front? Right, it canceled with a half in the double angle formula for the cosh. And then we integrate, we get pi t plus 1/2 the sinh of 2t 0 to log 2, which gives me pi natural log of 2 plus 1/2 the hyperbolic sine of 2 log 2. Let me talk about how to simplify 2 log 2 times sinh of 2 log 2 over here. All right, so this is really the sinh of the natural log of 4, right? Because 2 log 2 is log of 2 to the 2. 2 squared is 4. We can all agree? Yes? Okay. Okay, I feel better. Thank you. 1/2 e to the natural log of 4 minus e to the minus natural log of 4. All right, got a little bit more to do here. 1/2, that's just 4. And then this is e to the log of 1/4, right? So the log of 1/4 is, well, I mean, that's 1/2 of 4 minus 1/4, also known as 16/4 minus 1/4, known as 15/4, 15/8. Yep. So this gives us pi natural log of 2 plus 15 over 16. I mean, but come on, folks, right? If you look at this curve, right? I mean, just look at it. Obviously, the surface area of this curve is pi times the natural log of 2 plus 15/16. I mean, anybody can see it, right? But isn't calculus great? I mean, this is something that would have been like weeks on end in a wood shop to prove without calculus, right? I mean, like, can you imagine trying to do this? You build your hyperbolic curve, you turn it on the lathe or whatever, come up with, I mean, it would be a pain. You're like, I would use paper mache. Fine, you got me. You've greatly sped up the process. Very good, very good. But, okay, what else can we do here? Now that we've got this speed function and it's so snazzy and simple, maybe we should also try to figure out what's the centroid of this curve, right? Let's make the most of this example. What's the centroid of this little curve right here? Dare we ask this question? What's the arc length of the curve to start with? So the arc length would be what? Integral from 0 to log 2 of what is it? The speed, right? The speed here was cosh t dt. So it looks like we got a sinh of the natural log of 2, otherwise known as 1/2 e to the log 2 minus e to the log 1/2 which is 1/2 of 2 minus 1/2. That's 4/2, 3/2, 3/4. He's correct. Yes, no, maybe so? Yes? Okay. Then we can figure out the x-coordinate of the centroid by doing what integral? See here, x bar, 1 over L, which is what? I'll write it down, 1 over L, integral of x v dt. Okay, so let's put in what things are here. So that's really 4/3, right? Integral from 0 to log 2. What was x? Oh, t. Oh no. Hey, but you know, this is good. We need practice with this. Why do we need practice with this? Not to bring up a sore topic, but there is a final exam. It lurks in your future. Not too far in the future. And this is one of those things you'll definitely need to know how to do for the final, right? Integrate by parts. So here's your dv, here's your u. We get 4/3 t sinh t minus the integral of v du, which is sinh t dt. That has to be evaluated from 0 to log 2, 0 to log 2. You know, I'm starting to like this problem. There's a lot to it. So we got log 2, sinh log 2. Man, this is ugly. Minus the cosh of the natural log of 2 plus the cosh of 0, which is 1. That can be simplified. Let's see here. We figured out sinh of log 2 is what? 3/4, right? So this is 4/3 times the log of 2 times 3/4 minus, what's the cosh of log 2? Figure it out up here. So that's 1/2 of 2 plus 1/2. 1/2 of 5/2. 5/4. So minus 5/4 plus 1. So we can clean that up a little bit. That's the log of 2. This over here is 1/4, right? 1/4 times 4/3 is what? It's going to be minus 1/4. Minus 1/4 times 4/3 minus 1/3, right? So there you go. And that makes sense. That makes good sense because if you thought about this or not, but the x-coordinate here, of course, is what? This is log 2. This is log 2 minus 0.3. So that says this log 2 is, by the way, about 0.7-ish. So it says that the centroid is like somewhere here. That seems right to me. It should be closer to the place where it's growing fast as opposed to the place where it's more shallow. Like more of the curve is up here than is down there. You wouldn't be in the middle because there's more length as going faster over there. And how do you figure out then the other thing, y bar? You got two choices, right? Tell you what, I'll make this up to you. We're going to end 10 minutes early on Wednesday. Sound good? Nathan's like, that's no deal for me. I got to stay here. So we can either calculate, right? We can either just calculate y bar equals to 1 over L integral, y, which is what? Cosh t, 0 to log 2, then times cosh t dt, right? We could do that, or we could just do what? We could use the theorem of Pappus to figure out the y bar, right? Because the theorem of Pappus says that the surface area is equal to 2 pi y bar times the times L. So that means that y bar is equal to the surface area divided by 2 pi times the length, which in our case is that thing. Oh, I need one of these deals. Is that better? Okay, so, yeah, sorry about that. So pi times log 2 plus 15/16 divided by 2 pi L, but 2 pi L is really just 2 pi times 3 over 4, which is what? I'll just write it 2 pi. Let me just write it in an unsimplified way. So you could simplify that, and that will give you the y bar. Or you could do this integration, but you can kind of see why this is, right? To calculate, it's kind of stupid. This is the integral of cosh squared, right? Times 2 pi. And then we just found the formula that, y bar is 1 over L times the integral of cosh squared. So it stands to reason that the centroid's coordinate for the y and the surface area are directly related just by like a scale factor. You can see it, the same integral, right? With just this 1 over L here versus a 2 pi over there. Anyway, the fact that they're related in that way, again, is Pappus' theorem, but cool. I will shut up. See you tomorrow. And you guys really, you will not offend me if you ask questions about the homework tomorrow. Like, it's really allowed. Like, there's a whole chapter of homework questions.